Good day, students. For this lesson, we will have serum protein electrophoresis. For the learning objectives at the end of this lesson, you're all expected to identify the components of electrophoresis system, determine how electrophoresis works, and lastly, recognize the electrophoretogram patterns and their disease correlations. So what is electrophoresis? By definition, it is the migration of charged solutes or particles in an electric field, and the separation of these solutes or particles requires high voltage, usually between 50 to 200 volts. So that means the molecules that we are studying, usually we are studying proteins when we are using electrophoresis. So these molecules move in a medium. And usually we use a gel or agar for our medium. So we separate the protein molecules based on types or classes. And in order for this to happen, of course, an electric current is needed. That's why it is called as electrophoresis. So the term literally means migration with electricity. So the electricity is the power source. And this was first developed by Cellulose in 1926 for the study of serum proteins. So Cellulose is a Swedish biochemist who won the Nobel Prize in Chemistry in 1948 for his research on electrophoresis, particularly in his discoveries concerning the complex nature of these serum proteins. The two types of electrophoresis are the zone electrophoresis and iontophoresis. The zone electrophoresis is the one commonly used in the clinical laboratory, and this involves the migration of charged macromolecules. So normally we use this zone electrophoresis in studying proteins. And there is a support medium in which the molecules migrate, and normally it is a paper, a cellulose acetate, or agarose gel film. Another thing, we have iontophoresis, and this one involves the migration of small ions or micromolecules. So this is how the iontophoresis looks like. So iontophoresis is a transdermal delivery system in which we use a drug that carries a charge. So it could be a positive charge drug or a negative charge drug. So this drug is delivered through the skin by a low electrical current. And this is normally used to treat a condition known as the hyperhidrosis. So this is a medical condition characterized by excessive sweating. So as what you can notice here, a patch is placed on a skin. It's either on the palm or on the feet or even in the underarms of a patient. So that patch contains drugs, and it could be a positive charge drug or a negative charge drug. So the ions in the sweat, if it is negatively charged, it will be attracted to the positively charged drug. If it is a positive ion, then it will be attracted to the negative charged drug. So that is how iontophoresis reduces the sweating. So after migration and separation of those macromolecules in the zone electrophoresis, we can now visualize the patterns of separation of these proteins, and we call it as the electrophoretogram. So in short, this is the result of zone electrophoresis, and it consists of sharply separated zones of macromolecules such as this one. So you can see protein bonds, and normally after separation of these macromolecules using the electrophoresis in a support medium, we stain the support medium in order to visualize the bands. So it also looks like this one. Another thing you have to remember, opposite attracts. So the positive charge ions, we call it as cation, will migrate or will be attracted to the negative pole or negative terminal. So we call it as the cathode. On the other hand, the negative charge ions, we call it as anions. So they will be attracted to the positive pole or the positive terminal, and that is called the anode. The rate of migration of ions depends on the following. So first, the size. So between a small and a large molecule, it is given that the smaller molecules will migrate faster as compared to the bigger molecules. And next one, we have the shape. So the proteins, for example, could be globular or fibrous in shape. So between the two, it's the globular protein that will migrate faster as compared to the fibrous protein. Next one, the support medium. So this could be an agarose gel, this could be a cellulose acetate or polyacrylamide gel. So this medium also serves as the basis of the separation. Like for example, if we are using agarose gel as a support medium, then the basis of the separation and migration is the electrical charge. Whereas, if we are using, for example, the polyacrylamide gel electrophoresis, then the basis of the separation is the molecular weight or the size of the molecules. Next one, the buffer or ionic strength of electric field. So this reflects the concentration of ions in the solution. Like for example, you have a lot of ions in the solution of your electrophoresis medium. So that means you have an increased ionic strength. So that will now lead to an increased current which would release a greater amount of heat. So that will slow down or decrease the migration rate of the molecules. Whereas if you have a decrease or low ionic strength, then that will increase the rate of migration. So that's how the buffer affects the migration of the ions. Next one, the pH. So the pH of the buffer could be acidic or it could be basic. But first, you have to remember that proteins are ampholites. So an ampholite is a molecule whose net charge can either be positive or negative. Like for example, if a buffer is more acidic as compared to the isoelectric point of an ampholite, then it will bind hydrogen ions. So what will happen now to the proteins? So the proteins will become positively charged. So we call them as cations. So they will migrate towards the negative pole, which is the cathode. Whereas, if the buffer is more basic as compared to the isoelectric point of the ampholite, it will lose these hydrogen ions. So the proteins now will become negatively charged, and we call it as an ion. So where will they migrate? So those anions will migrate to the positive pole, we call as the anode. So that's how the buffer and the pH affects the migration of the molecules. And lastly, we have the net charge, which is also known as the total charge the total charge of an ion in a solution. So it could be again positive or negative charge, and it's dependent again on the pH of the solution. For the uses of electrophoresis in the clinical laboratory, first, we use it in studying proteins. So we use serum, urine, CSF, or other biologic fluids for this one. Also in the separation of the types of hemoglobin, of the tissues, and of course of the isoenzymes such as the creatinine kinase, lactate dehydrogenase, and alkaline phosphatase. So the isoenzymes catalyze the same reaction to enzymes, but they differ in structures. Next, for the components of electrophoresis, first we have the driving force or the electrical power. So without this, the electrophoresis will not work. Next one, we have the buffer. So that determines the ionic strength of the solution. So the buffer could have an increased pH, which is basic, or a decreased pH, which is again acidic. Next one, of course, we have the sample or the specimen, the support medium, which holds the sample and provides the path for migration. And next one, we have the detecting system. This one shows the basic components of electrophoresis. So let's see how this entire system works. So of course, first you need a sample. It could be a urine, plasma, serum, or CSF that you have to transfer in the wells located in your support medium. So you have to pipette it and you place that in the wells. After that, you turn on the electrical power, and the voltage generated by this electrical power will make the ions in the buffer solution in your electrophoresis move, and that movement will cause now the migration of the molecules or the proteins present in your specimen. So they will be separated as bands. So you can now remove this support medium and stain it, and then you can visualize now the electrophoretogram patterns. For the types of support media, first we have the paper. So this is commonly used before. However, it offers a lot of disadvantages. So it's fragile, easily damaged, and porous. That's why it's replaced by other support media which are more stable. Next, starch gel. So this is also fragile. There's an inability to store permanent results, so it will be hard to retrieve old specimens or old records of patients, and the gel needs to be prepared in-house. So it's a bit laborious to use this one. Next, cellulose acetate. So this support medium sets the pH of the buffer at 8.6. So this is a basic solution, so that means the proteins are negatively charged. And these negatively charged ions, of course, will migrate to the positive pole, the anode. And one of the disadvantages of this cellulose acetate is it is extremely brittle when dried. Another thing, the strip can be cleared of cellulose acetate, leaving only the protein bands on a transparent background. And because it's transparent, you can use stains or dyes in order to visualize the proteins on that transparent film. So the most commonly used stains, we have the Poncho S and Amido Black. That's for cellulose acetate. Next one, we have the agarose gel. So this is made from seaweed and it has an electric neutrality. So that means there is a minimal electric charge on the agarose itself, so there's no interaction on proteins. And because of this, because of electric neutrality, the separation takes place strictly on the basis of electric charge, as I mentioned earlier. And also, just like your cellulose acetate, the buffer is set at 8.6, so the proteins are negatively charged. So for the stain of choice, we have Amido Black, and if your specimen is a CSF, then Kumasi Blue is the stain of choice. Lastly, we have the polyacrylamide gel electrophoresis, or the PAGE. So the major factor in separation process using the support medium is the molecular weight or the size of the molecules. So this one is composed of acrylamide polymer and a long chain molecules which cross-link to a certain extent. So it contains a network that will trap the molecules in the gel, especially if the molecules have a large size or molecular weight. So the larger the protein polypeptide, the slower it moves. So we can use this to study lipoproteins, hemoglobin, and isoenzymes. So this illustration shows the setup of the polyacrylamide gel electrophoresis, or the PAGE. So as mentioned earlier, the PAGE itself, or the gel, contains acrylamide polymer or long chain molecules which cross-link to a certain extent. So let's just imagine that in this gel, we can find cross-links. And what is happening here is that the proteins present in the sample are first denatured with anionic reagent. So the anionic reagent that we are using is commonly the SDS, or this is what we call as the sodium dodecyl sulfate. So this SDS molecule is negatively charged, and after adding SDS, the sample is then heated, so that will denature the proteins. So the SDS will now bind to the proteins and cause them to unfold. So if the proteins here are present in your sample, the SDS molecule will unfold those proteins. And what will happen now, since the SDS molecule is negatively charged, it will coat the unfolded proteins. So for example, you have an unfolded protein here. So this will be coated by a negatively charged SDS molecule. So that means the proteins have all similar shape and charge to mass ratio. And another thing, if the proteins contain different subunits, the SDS will not only unfold the proteins but also dissociate the proteins to its individual polypeptide chains. And another thing, after this one, after denaturation of proteins, the proteins are then transferred into a tube and loaded to the polyacrylamide gel medium. So you will put the sample here. And next one, the negative charge polypeptide, because the SDS is negative, the proteins will become negatively charged, right? So the negative charge polypeptide will migrate to the positive pole or the positive terminal. This is the anode. And since there is a presence of cross-link in the gel itself, we have here, for example, large polypeptides and small polypeptides. So what will happen now? Between the two, of course, the smaller polypeptide will travel faster towards the anode as compared to the larger polypeptides because of its large size. So that means the smaller polypeptides can travel more easily through the pores or networks in the gel than the larger polypeptides. And because the polypeptide has a similar charge, so what will happen? The migration is only dependent on their size or molecular weight. So that's the principle of polyacrylamide gel electrophoresis. So after processing the proteins, after separating them and letting them migrate in the support medium, what will happen now is that we can stain this support medium and then visualize the protein bands. So this one shows the normal electrophoretic graph of blood proteins. And also we can plot it using this chart. And as what you have noticed here, the band which is the darkest is the albumin, because albumin is the most abundant proteins present in your blood. So that's why it's found the darkest in the electrophoretogram. To easily remember the normal electrophoretic pattern of the proteins in the blood, just remember this analogy. Albumin is attracted to the anode because of his positive attitude. So take note that the anode is the positive pole or the positive terminal. That's why albumin is attracted to it, because in this case, albumin is the most negatively charged among the protein fractions, especially at a basic pH where proteins are negatively charged. Like for example, at pH 8.6, proteins are negatively charged. So they will start migrating at the negative pole, which is the cathode. So the direction of the migration is towards the positive pole, which is the anode. Another one, we have the relative percentage of protein bands. So as what you've noticed here, albumin is the most abundant protein present in the blood, and the list is the alpha-1 globulin fractions. And also we have a list here of the significant proteins in electrophoretic fractions. So sometimes we can also observe the pre-albumin in the electrophoretogram pattern. So this pre-albumin is an indicator of poor protein nutrition, and it is termed as pre-albumin because it migrates ahead of the albumin. Next one, we have also the detailed list, the zones, and the fractions of proteins found in each zone. And also this one. So let's have some of the patterns that we commonly encounter when we use the electrophoresis system. So first, we have the pattern of acute inflammation. So in this one, the albumin is decreased. So just remember, this is just a relative decrease because there is an accumulation of fluid in cases of inflammation. Next one, the alpha-1 and alpha-2 regions are also increased during inflammatory response. This is due to increased hepatic synthesis of acute phase reactant proteins, which are primarily found in the alpha-1 and alpha-2 regions. Now let's have the pattern of nephrotic syndrome. So in this condition, there is a massive urine protein loss, which is due to the increased permeability of the glomerulus to protein. So as what you notice here, almost all proteins are decreased except the alpha-2 macroglobulin region. So the increased permeability of the glomerulus may be minimal, so that only albumin and other smaller molecular weight proteins are selectively filtered, or it may be greater so that larger proteins are also filtered, as is the case in this example. And the obvious pattern here is the increased macroglobulin. So the name itself tells us that the macroglobulin is sufficiently large so that it is not filtered by the glomerulus, and the increased synthesis, of course, from the liver also causes its accumulation. That's why you have an increased alpha-2 macroglobulin, whereas the other proteins are decreased. Because of the massive protein loss, almost all proteins are decreased in the blood. Thus, they can be already found in the urine sample. That's why we can see a lighter staining electrophoretogram pattern here if we are using the serum sample as compared to the urine sample with darker bands. So that's for your nephrotic syndrome. And also, you have to remember that in your blood, you can find different classes and sizes of proteins. Some of the proteins are very large, whereas some are medium in size or very small in size. And remember, in nephrotic syndrome, there is an increased permeability of glomerulus, right? So that means the glomerulus continually filters the protein in the blood. That's why they leak out in the urine, particularly those which are smaller in size. So you can find them in your urine sample. That's why if we check the blood sample of a patient with nephrotic syndrome, we can observe decreased amount of low molecular weight proteins. But the high molecular weight proteins are increased. It is opposite with the urine sample, because in the urine sample, the high molecular weight proteins are decreased, whereas the low molecular weight proteins are increased. Next, we have the electrophoretic pattern of liver cirrhosis. So the characteristic pattern of this is the beta-gamma bridge. So this one, as what you can observe, the proteins are decreased. So the albumin here, the alpha-1 and alpha-2 are all decreased. But what is unique here is the beta-gamma bridging, because this is due to the enhanced production of immunoglobulin A. In the pattern of monoclonal gammopathy, we can see a tall spike in the gamma region, or we call it as the gamma peak. So this is indicative of a disease known as multiple myeloma. So myelo, that refers to your bone marrow. So in this condition, there is an increased production of immunoglobulins by your plasma cells. But these immunoglobulins or antibodies are non-functional. So they are increased in numbers. That's why you can see an increased gamma region in the electrophoretic pattern. And another one, when we say monoclonal gammopathy, that indicates the secretion of exactly the same form of immunoglobulin, and you have this M protein present in your blood or your urine sample. And also you have here the electrophoretogram. So this one is the opposite of monoclonal gammopathy, because you can observe here a decreased gamma globulin region. And in the monoclonal gammopathy, you have a tall spike in the gamma region. So this is what we call as the hypogammaglobulinemia. Hypo means decreased. Gamma globulin in the blood. The suffix emia means conditions relating to the blood. So the hypogammaglobulinemia is a type of primary immune deficiency disease, and usually this is genetics. And this is characterized by a reduction in all types of gamma globulins. That's why you have here a decreased antibodies in the gamma region. Next, we have the alpha-1 antitrypsin deficiency. So the alpha-1 antitrypsin is a protein that protects the lungs, and it's the major component of the alpha-1 band. So this illustration would tell us that the alpha-1 antitrypsin is a protease inhibitor. It inactivates your elastase. On the other hand, your elastase is an enzyme. It's a protease that breaks down other proteins such as the elastin present in your lungs. So if the alpha-1 antitrypsin is present, the elastase cannot break down the elastin. But if there is a deficiency in alpha-1 antitrypsin, the elastase will break down the elastin. So that will now cause lung diseases such as COPD and emphysema. So that's the consequence of having this alpha-1 antitrypsin deficiency. And in addition to that, the deficiency in alpha-1 antitrypsin can cause damage to the liver because abnormal alpha-1 antitrypsin can also accumulate in the liver and damage this organ. And if the alpha-1 antitrypsin proteins are not the right shape, they got stuck in the liver cells and they can't reach the lungs. So it further damages your lungs. So that's for your alpha-1 antitrypsin deficiency. So that ends my presentation. I hope no one's lost. Thank you.